So it's my pleasure to introduce Professor Katie Breivik, who is an assistant professor at Carnegie Mellon University. And before that, she was a postdoctoral fellow at the CCA at the Flatiron Institute in New York. And before that, she was a CITA fellow here. So yeah, Katie is an expert on compact objects and all sorts of systems, and she'll be telling us about some of that today.
Yeah, thanks, Ryan. Thanks for the intro. Fun to be back giving a seminar in person. Yeah, I don't know what I was gonna. Once a citizen, always a citizen, right? Statement. It's been super fun. I've had some fun chats with people already today. I will be kind of around tomorrow, but if you look at my schedule, it's totally whack because I blacked out a bunch of it. So send an email if you want to chat. I'll be around at the Transients Conference next week, but I'm sure we can find a time to chat if anything that I say here piques your interest. So today I'm going to be talking pretty focused on just this one type of population, which has now been named, I think, conclusively dormant compact object binaries. And the reason that they are dormant is because you don't see any indication of the compact object existing in the binary. Okay, so before we get into that, I want to go through just some of the reasons why I think that these things are interesting, and we're going to start with a statement that at this point I think is actually now not controversial, but the first time I made this slide was relatively controversial. So back when I started as a CITA fellow, people weren't really thinking about binary stars too much. And I guess that was good for me, good job security. My statement that I hope everyone leaves with, if you leave with nothing else, is that binary stars are likely a critical component of your research now, or will potentially be a limiting factor in your science in one way or another. No matter what kind of astronomy you do. I believe this very strongly. And so far, I have yet to meet a single person for which I couldn't at least make a tacit connection to your science case. In particular, for people who are looking for exoplanets, a lot of your main noise sources at this point in time in huge data sets that are finding exoplanets are binary stars. So if we understand the binary stars, that's very helpful for the exoplanet people. Another interesting connection here is actually for folks who are interested in dark matter and cosmology. One of the largest systematics in finding clumpy dark matter in stellar streams like you see here is actually the fact that you can't really tell the difference between some of these stars having motion due to a perturbed clumpy dark matter particle, who knows what it is, but something that's perturbed the system, or if it's just a wide binary that happens to have perturbed the star. So binaries are everywhere. You may not be interested in understanding how they work for your own science, but please don't forget about them because they're very important. Good. Okay, so that's the motivation for why I do what I do, which is binary stars. Today, I'm going to be talking about a very specific population, but I think it's useful, given that many people don't work on binary stars in their everyday life, to just kind of give you a lightning speed run through of ways in which we make compact object binaries, starting from a pair of isolated, just two stars on their zero-age main sequence. When you have stars on their zero-age main sequence, all they're going to do for the vast majority of their lifetime is burn hydrogen into helium, right? That's what stars do, fine. When they do this, their radii don't change very much. Whatever properties they start out with here, they're going to mostly maintain unless the orbit happens to be very eccentric, in which case maybe tides can do some work, but probably not. The radii aren't changing very much. However, eventually, the more massive star is going to exhaust hydrogen in its core. It will fill what's called the Roche lobe, which is the potential at which mass that goes beyond that radius is no longer bound to the system. When the star fills its Roche lobe, It has a couple of different options that can happen. One of the, and actually these, the way that you decide for what's gonna happen depends both on how the orbit responds to mass exchange, but also how the donor itself responds to that mass exchange. One of the ways that this can go is into something that we call stable mass transfer. And this tends to happen on thermal timescales for the stars. It often happens when the donor has a radiative envelope instead of a convective envelope. The reason for that is because radiative envelopes, when they lose mass, they tend to shrink a little bit, and then that just nicely traces the Roche load. If they're convective, something else happened. In this mass transfer process, because we're starting with a more massive star, the orbit's initially going to shrink until you reach a mass ratio of 1, in which case the orbit then begins to widen because you're donating from a less massive star to a more massive star. So in general, these types of systems don't have like maximal shrinking. They can widen a bit. And on this thermal timescale mass transfer, eventually what happens is you end up with a fully stripped helium star, this little blue guy here, and a likely more massive secondary than it started out with. Probably there's a significant amount of mass that can be accreted. However, we're not totally sure what the answer is for this, but we can parameterize it. Once you have completed the mass transfer and you have your strip star, the evolution of that initially more massive star is going to proceed pretty rapidly, and eventually the star will reach core collapse. When it does so, it may explode, it may not explode. That is an extremely active area of research that requires immense scale calculations that I personally don't do. The thing that I take into account is if there is an explosion, that will be imprinted by momentum kicks, we call natal kicks, into both the size and shape of these orbits. So both the eccentricity and orbital period will change significantly, and we can actually just perfectly, through kinematics, work out, given a natal kick, what does this do to the orbit? So that's something that's not particularly uncertain. The thing that's uncertain is how big is the kick and what direction. Okay, now, somewhat unsurprisingly, we now have our secondary star that's going to exhaust the core hydrogen as well and fill its Roche lobe, and that can also remain stable here. The main difference between this stable mass transfer and this stable mass transfer is mass transfer onto a compact object likely reaches Eddington limits pretty quickly. So rather than donating upwards of tens of solar masses to the companion, that mass is just going to be lost from the system. The compact object isn't going to gain a significant amount of mass. Because of that, the orbit will change a little bit differently. It's not going to do this really big dramatic shrink and widen. That will be kind of suppressed, that orbital change. Good. Okay, so then we again can reach our strip star phase. The strip star will then also reach core collapse, potentially with a kick or not. By the time you get to double compact object formation, the only thing that's at play here is going to be gravitational wave emission, which will shrink and circularize your orbit until eventually you merge, producing the gravitational waves that ground-based detectors have detected hundreds of systems for at this point, right? This is one pathway. From here, you could also go into a different pathway, and that's what I was talking about a little bit before. If the mass transfer becomes dynamically unstable rather than remaining stable on a thermal timescale, you go into something that we call a common envelope evolution. This is far and away the most uncertain thing that happens in binary stars. We don't really know how common envelope works, but we do know that stars go through it because we see the products of common envelope, which are these post-common envelope binaries. They're strip stars in usually much closer orbits than you would expect from, say, a stable mass transfer configuration. And importantly, because it happens on a dynamical timescale, the products come out much faster than you would expect on from stable mass transfer. They also tend, like I said, they tend to be closer. The reason for that is that you don't have this mass ratio reversal that can happen. You're just really shrinking the orbit as this, say, compact object spirals in, eventually unbinding the envelope. I should also say, it is possible to just have the two cores merge and you don't have a successful envelope rejection. That's also definitely a possibility. Good. Okay. Again, strip star maybe has a kick, maybe doesn't, we're not sure. Then you shrink and circularize, producing gravitational waves. Notably, this is all cartoons in Keynote. That's because I don't have beautiful images to show you necessarily of all of these things. But what I want to point out is that several of these phases have been directly observed. Some of them by people in the room, which is cool. And what I really want to point out here is, importantly, the oldest reference that we have on this slide is 2012. The vast majority of the things that we have as detections of these different phases are post-2020. And that's because we're genuinely undergoing a revolution in how we observe binary star populations, and that's because we finally convinced people to let us observe the same stars over and over and over again, and they finally gave us the money to do it, which is like, we love that. And also gravitational wave detections, which clean up this area. So part of the reason why I am still showing cartoons here and can't tell you exactly what fraction of everything happens is we've just barely gotten our hands on a lot of this data, and we're only now starting to scratch the surface. Yeah, and now just for completeness, I will show nothing. This. So you could, in practice, also go straight into common envelope. This basically tells you everything you need to know about what binary stars do, modulo some extremely important physical things that happen, like tides, magnetic braking. There's tons of stuff that goes in there, but what I want you to take away from this is, one, Roche overflow mass transfer through either stable or common envelope is the dominant uncertainty, I think, in the binary star evolution. And two, the compact object formation mechanism plays a very critical role in both the characteristics, like the shapes of the orbits, but also the formation rates of neutron star and black hole hosting binaries. The way I like to study this is through something called binary population synthesis. Binary population synthesis is a tool that simulates stars through all of the phases I just walked you through, using some type of model for single stars, and then pasting over analytic theory for how binary star interactions will alter the orbit. And we basically do this many, many, many times as a way to study how uncertainties in the physical processes that we can incorporate from binary star interactions shape stellar populations across each of those phases that I showed you. The way that I do this personally is through a code that myself and others, you can see other authors here, worked on for the better part of my thesis while I was at Northwestern. The code is called Cosmic. If you want to Google it, you have to Google Cosmic PopSynth. If you just Google Cosmic, you're gonna get like 1,000 other links. Students in the room, don't try to make acronyms that are fancy and lovely. Just pick a name for a code that's easy to Google. That's my advice. So Cosmic is one of many codes at this point that are openly developed population synthesis codes. The thing that I think sets Cosmic apart is first and foremost, we actually have integrated directly with the globular cluster dynamics code so that when you're running stars in globular cluster dynamics code, like the one that Claire uses here, you're actually using Cosmic to evolve those binaries. That means that we can do self-consistent comparisons in dynamical and isolated environments. The other thing that I think sets Cosmic apart is that we spend a significant amount of our time just developing the user interface so that anyone who has a laptop in this room can pip install Cosmic and simulate 10,000 binaries by the end of this seminar, probably. So if someone wants to take me up on that, let me know. I've had it happen before. Everything is documented. You can see our docs there. So far, Cosmic has been used in a bunch of studies that you can see here. A lot of us are really excited about black holes. That's what all of these are. These are the dormant black holes, isolated binaries, globular clusters. But Cosmic can also be used to study, for example, blue stragglers, CV populations, X-ray binaries, double white dwarfs, any type of stellar population that you can come up with. Probably there's a calculation that might be useful to calculate the rates of whatever binary population you're interested in. And that's usually why people will pick up the code and use it. Today, I'm just talking about the dormant population here, the non-accreting compact objects. But I want to highlight that I'm generally excited about all kinds of binary stars. I'd love to talk to you about white dwarfs and neutron stars. One thing that I'm not going to talk about at all is gravitational waves, but I spend a lot of time thinking about gravitational waves. And in particular, I would love to convince you why LISA is going to be a really awesome, important thing for you some other time. And finally, I have opinions about open software. So if you want to chat about that, we can always chat about that. Okay, good. That's my run through of the tool that we're using, population synthesis and binary stars. As a reminder, the thing that I'm interested in is trying to understand binary star interactions. And in doing so, I think the way that I personally think about doing this is thinking about individual phases of evolution, say accreting binaries or these dormant detached binaries. And if you want to compare your data to your simulations to see what you can constrain in binary star interaction, one thing that's useful to note is that the farther along you get in this evolution sequence, the smaller your orbits are. So if we're, for example, trying to observe these guys, we're going to have different size orbits than if we're trying to observe these. Not so surprising. But more importantly, the more advanced you get in these evolutionary phases, the actual physical size of the population per unit initial detached binary star formed decreases significantly. And so to make this point, say you start out with a massive star that's massive enough to make a black hole. It's going to be a pretty small fraction of all the stars that are formed, right? Now, in the process of getting to the detached black hole star phase, you will go through a mass transfer, probably. That mass transfer 30% of the time results in a stellar merger. And then 90% of the time, depending on how strong the kicks are, results in an unbound binary. So by the time you get to the detached black hole star phase, you're looking at a very small portion of the total star formation. And by the time you make it all the way to the gravitational wave sources, we're really scraping at the tails of these initial distributions. If you want to be more gentle with the numbers, you could just take massive stars, but still, even at the gravitational wave edge of this, we're only looking at something like 0.5% of all massive stars that are ever formed. So part of the reason why I'm not telling you about gravitational wave, which is something that everyone's really excited about and it's amazing, is because I'm actually really just interested in understanding binary star interactions, and I don't necessarily care what the phase is. So for example, if this is 5 to 50% of all of the massive stars, maybe we'll learn a little bit more about the interactions that get you from here to here that can then help us understand what's happening all the way over here. So that's kind of the motivation. There's a huge hole here for X-rays. We don't know exactly how many of these things there are, and the reason for that is a selection function. So in this region, where you are finding compact objects because of the stuff that they're accreting, that's a really tough game, because sometimes they launch giant X-rays from these big, beautiful accretion disks and everything works out. Sometimes they don't, and we don't really know how often that happens. We don't know the duty cycle at which this happens. And so X-ray binaries, while being fantastically interesting populations, are extremely difficult to characterize in a population sense, because we just don't know how often we should be detecting them or not. Good. Right. Okay, so in terms of just thinking about ways to discover these types of systems, at this end, really what we're looking at is large-scale surveys, photometric variations, astrometric measurements, and radial velocities. I'm going to focus just on astrometry and radial velocity. And of course, at this end, gravitational waves pick up all the rest. So, good. Okay, any thoughts or questions so far? Because I'm about to jump straight into dormant black holes. Yeah.
In the last one, I didn't catch what's the difference between the 1% and the second.
Massive stars versus all stars.
Oh,
Yeah.
Okay.
Cool. Okay, good. Let's talk about dormant compact object binaries. So the idea here is genuinely just, if a black hole or a neutron star has a stellar companion, we can see the star, and it's going to orbit in some way. One of the ways that you can do this is by taking radial velocity measurements of the compact object binaries. So you take a spectrum, you wait a little bit, you take another spectrum, you wait a little bit. Eventually you make your many radial velocity measurements. And if you cover the entire orbit, you'll have an orbital period measurement, a semi-major axis measurement, an eccentricity measurement. You're probably not going to get this inclination though, which is really annoying. You're not going to know this direction, you'll just see this, right? If you make lots of radial velocity measurements, you can put them into a semi-amplitude, that's what this K is, and then have this mass function for your compact object. That sin I comes in here. This is really annoying if you're trying to find black hole candidates, because if you're viewing something that's like this, and it's doing this, that's pretty massive, but if you're viewing and it's totally edge on and it's doing this, it's not very massive. So this inclination can be really annoying. The idea of finding compact objects, though, is not a new one. I'm certainly not one of like the first 20 people to think about this. Virginia Trimble and Kip Thorne actually have papers on this going back to the 60s. So it's been known that if you just hammer with radial velocity surveys, you're going to eventually start to turn out these compact objects if they exist. Thankfully, the team led by Benjamin Giesers was awarded time with the MUSE instrument, and they launched NGC 3201. That's this globular cluster here. It's a globular cluster around the galaxy, and they found 2 black hole candidates that you can see here. They're both pretty lowish mass in comparison to the X-ray binaries. A lot of the X-ray binary black hole masses are right around 8. They're fairly eccentric. This one's quite eccentric. This one's going to be less so. But importantly, Saurabh Chatterjee and Kyle Kramer did some work to see whether or not they can produce globular clusters with their CMC simulations that create black hole main sequence binaries. And indeed, Kyle found that he absolutely could. He basically made these NGC 3201 binaries. And the really interesting thing is actually that if you take, this is the brightness profile of the globular clusters that they simulate. And if you match NGC 3201's brightness profile, they indicate that NGC 3201 has hundreds of black holes in its core, which is really, really cool. So being able to use these black hole main sequence binaries as tracers of a significant population of black holes in the core, I think is a really awesome use case for these dormant black hole binaries. I'm not going to talk too much more about this because I'm actually not an expert on this kind of stuff. Lucky for you, you have an expert on globular clusters here. Claire is a member of the CMC team as well. After 2018, there were 3 other low mass black hole candidates claimed from other surveys. This one was actually not a radial velocity survey. This was a photometric variation one. But these 2 were radial velocity discovered. And this effort was largely led by the Ohio State team that Todd Thompson and Chris Kachenik have been working with. And Thurindu did a lot of heavy lifting for a lot of this. Unfortunately, these 2 ended up being false positives, which is tough. I'll show you why it's tough. So when you are looking for compact objects orbiting bright stars, one of the first things that you have to do is take your spectra and say, okay, given this data, are there 2 components or 1 component to the spectrum? And like, if you had just given me that, I certainly, as a theorist, would have been like, I got nothing, guys. And so a lot of teams didn't have this expertise that were doing these searches because it's a relatively narrow band of expertise. So Kareem El Badri, who was developing his spectral disentangling code, kind of came in and cleaned up on a bunch of papers, being like, that's not a black hole, that's not a black hole, that's not a black hole, because he had his spectral disentangling code. One thing that's great is that after noting that this is something that's going to be a huge problem for all of these radial velocity surveys moving forward and general surveys moving forward, Kareem and a team led by Reese Seeberger in Hans Walter's group have now released like automated ways to do this analysis so that when we get SDSS5 data coming out like crazy, they don't have to have one person do all of this. So that's good. Story continues. In 2022, Tomer Shanar, who was working with the ELT Flames Tarantula survey that like Hugsana and others have been working on, Tomer turned out what is probably the farthest away dormant black hole that we will know about, because this one's in the big, large Magellanic Cloud. And you can see here that it's constrained relatively well. It's actually very similar to the X-ray binaries that we're aware of in the galaxy. It's a fairly short orbital period. The eccentricity is basically close to 0. 10-ish solar mass black hole, 25-ish solar mass star. They don't have great constraints because massive stars are much more difficult to model than like a solar type star with the spectra. So we know about this system as well. And as a heads up, there are much more types of these systems that I think are going to be hiding in SDSS5. So Michaela Weller and Jennifer Johnson did some great work to forecast what types of systems SDSS5 should be able to turn out. And in general, the reason that SDSS5 is going to be great is because it goes to hotter stars than our surveys generally go to, especially Apogee, for example, was really sensitive to one solar mass giant stars and almost nothing else because of its color cuts. SDSS5 has much hotter colors, so we'll pick up these more massive stars. Okay, that's radial velocity binaries. Now let's get to the stuff that I'm super excited about, which are the astrometric compact object binaries. So the idea here is not take a spectrum and measure radial velocities. Instead, the idea is measure the physical position in 3 dimensions on the sky as the star traces out its orbit, and you'll measure the semi-major axis of the luminous companion. The less massive your luminous companion gets, the closer this projected separation becomes to just the semi-major axis of the binary. Importantly, if you make lots of astrometric measurements and you can measure the orbital period, you don't have an inclination degeneracy. So astrometric orbits are really great for finding black hole candidates because you don't have this radial velocity struggle of a minimum mass that you're going against. Cool. I wouldn't be telling you about this if there wasn't a machine to do this. Gaia is a space telescope that was launched, I think over a decade ago at this point. And Gaia is measuring, I forget to change this every time. That's a 9. Gaia is measuring the positions and velocities of more than 1 billion stars in the galaxy. It has a ridiculous amount of science cases that go with that. Just knowing where stars are and how bright they are can tell you a lot of things. For me, Gaia is a binary finding machine. And so the idea here is this is 4 different panels of a 1 solar mass star orbiting a 1.4 solar mass neutron star. And what you see in this red arrow, that's the center of motion of the binary. And it's traveling with these proper motions that you can see here, 10 milliarc seconds per year. So the binary is moving around, or moving with some speed on the sky. Now, Gaia watches things as it orbits around the Earth on a 1-year cycle. It doesn't orbit around, well, yeah, it orbits around the Earth, and the Earth goes around the sun to make parallax measurements. And so on this very short period side, what you see here is mostly the parallax going on, and then the binaries create these little added motion to it. On this side, this is the parallax, and the binary motion is creating not like as, you don't see as much of it, right? On this, in here, this is actually where all of the action is. Gaia is very sensitive in here because you could subtract out the parallax motion and you just see these huge orbits. That's how we're finding all of these things. So with this in mind, because I'm a theorist, I'm a simulator, I didn't go searching for this data right out of the gate, and also we didn't have it until 2022. So what I've been spending a lot of time doing is thinking about simulating this dormant compact object population. And to do that, we use Cosmic to do the binary evolution. We assign metallicity dependent positions and ages with cosmological zoom-in simulations. We can have a lot of conversations about whether this is a good idea or not. And the answer is, I think it's probably not a good idea. And we're moving toward empirical distributions here. But prior, I'm looking at Nesh, Nesh and I have talked. Good. So we get some metallicity dependent positions and ages. We evolve them with binaries with Cosmic, and then we try to place as faithful of a population selection criteria as we can to do the Gaia synthetic correction. That means we make sure that they're bright enough to see in Gaia, having been reddened with a dust model. We make sure that the size of the orbit on the sky is big enough for Gaia to resolve. This is a relatively conservative constraint. We make sure that the orbit will close in a 10-year observation time, and we require that the black hole mass be greater than 3 solar masses. This is actually also, sometimes we're even more conservative, and we require that the black hole mass be greater than the mass of the stellar companion, so that there's no question. From some of these simulations, we've started to gather general rules of thumb. There's 2 big figures on here. The first thing that I want to point out in these figures is on all of them, they're all showing log orbital period. And in every single model, there are 2 giant pumps, right? On this side, there's no common envelope and really almost no interaction at all. And on this side, basically everything is common envelopes. This is because Gaia is sensitive to stars that live longer, so have lower masses, and therefore are more likely to undergo a common envelope evolution than their more massive, stellar cousins. So most of what Gaia sees is probably going to be some type of post-common envelope interaction. The other thing that we see is, so this figure has a lot of panels. The top row, this is constant star formation and solar metallicity in the thin disk. This is to represent the old stellar populations in the thick disk. This is at 15% solar metallicity and a single burst of star formation. And what we've done in each column is we've increased our kick strengths. Column A has no black hole kick strength at all. The only type of kick that you would receive is if the black hole loses mass. We call this a Blau kick. And if you just lose mass quickly, that's going to add some momentum to your orbit. Up here, we assume that black holes get the same kicks as have been observed for pulsars. So really strong Maxwellian 1265 kicks. And here, we assume that they get pulsar kicks, but then if mass falls back onto the compact object, that's going to linearly reduce the momentum. Okay. From here to here to here, you decrease the size of the population by an order of magnitude. So natal kicks significantly wipe out, in particular here, the population. So both common envelope and natal kicks are playing an enormous role in what's shaping this population. Some other things that we have learned is most companions to black holes are old and subsolar metallicity. That's again because the more likely you are to stick around as a star to be picked up by Gaia. If you take every star that's low mass, it's going to hang out in the galaxy for us to observe it today. That's basically it. We'll see some of these younger populations here. The reason that you get this rise is because the bigger stars that are younger are brighter, so you can see them farther away. Good, so that's one statement. The other statement to make is that there are going to be many more neutron stars than black holes. The reason for that is just an initial mass function argument, more or less. There are way more 10 solar mass stars that are formed than there are 40 solar mass stars. Easy. That is genuinely what gets you between these 2 models. Cool. Okay, those are predictions. Those are statements that we made. Gaia DR3 came out in 2022. We were super excited at the Flatiron for it to come out. And this was the first figure that I saw that Kareem texted me when I was on the subway going into work. He was like, something happened to the Gaia data that we don't totally understand yet, but you need to start placing this cut, this black line here, because DR3 for the astrometric binary data set only contains systems that are above that line. So what ended up happening, we can talk through this data. This is an orbital period measurement. This is parallax SNR. You can see something bad is happening here. They came in as like spuriously large, high mass functions. So they were like, wow, there's a bunch of like weird high mass measurements coming in here. We don't really know what to do with it. And the Gaia astrometric binary team has 6 people on it. And they were like, DR3 is coming out. You got to do something. And so that's what they did. They just were like, what is the most, like, how can we get rid of the least amount of data with something that people can put a selection on? So that's what they did. For people who are wondering what this feature is, this is real. This is Gaia's insensitivity to year-long orbits, because it's measuring parallax, and parallax happens at 1 year. Okay. So this was our first thing that we were paying attention to, because Kareem and I were really like excited to try to find these black holes. And this was the figure I made. I took Chirag's predictions from 2021 and it cut everything out. And I was like, damn, like, I have never been deflated more quickly in my career. Yeah, so I was like, let's hit the bar at 2 p.m. today instead of celebrating at like 8 p.m. Luckily, Kareem wasn't so fast to hit the bar. So he started this hunt where through some conversations, we basically decided, and like everyone at this point had decided, the way to find these types of compact objects is to look at the physical size of the system relative to its orbital period. Because if you're a low mass star orbiting a massive thing, you're going to be orbiting quickly, but you're going to take huge orbits compared to if you're like roughly equal mass. So you can see that here. These are just normal binaries. If there are triples, so say like 2 close stars and 1 wide star, that's here. The neutron stars, you can see start to creep up, but a 10 solar mass black hole with like a 1 solar mass star is just screaming above the data. So Kareem made this figure of all the systems who had mass functions roughly greater than 3 solar masses, and he said, like, let's hit it. Let's start pointing telescopes. Kareem and Keith Hawkins were basically sending all the telescope directives, and they basically started hitting all of these, but they went for these ones first because you're going to characterize the short period ones way easier, way faster than these guys, right? And lucky for Kareem and all of us, a supernormal G star happened to be in one of those sources. This is, he basically took for the paper, this is just some really boring, like 0.6 solar metallicity G star. That's what the star that's orbiting what we now have called Gaia BH1. He subtracted their flux, and you can really see it's just like, it's like a really boring G star, which we love. That's exactly what we want. He continued to make measurements, and there we go. He found it because we have the star. Find it. It's very easy to find when you put a star on it. Good. So he did astrometric follow-up. Several people helped, and in doing so, because you could model that G star, it's just like very obvious what it is, what its mass is. You could do excellent spectroscopic follow-up with many, many different instruments, and then you get ridiculously tight mass constraints. And so you can see here those errors that we have on the black hole mass orbital period eccentricity. Gravitational waves eat your heart out, is what I have to say to that. This is bonkers how well these are measured, like truly. So this is what they found. As a theorist, I sprang into action to make giant corner plots, because what else are we good for? And what we did is we took the measured orbital period, masses, eccentricity, and metallicity. We took cosmic, and we combined the initial binary parameters with common envelope parameters and kick strengths and directions. And we mapped all of those jointly to say, what do you have to do to make a Gaia BH1 binary? We started to run into problems basically immediately. So the present day mass ratio is about 10 to 1. That means that because it had to go through a common envelope, the zero-age main sequence mass ratio is like 70 to 1. We've never seen that before. So who knows if that's realistic or not, but usually when we look for massive stars, we see massive companions. So this is either a very exciting thing or maybe just not realistic. Similarly, maybe exciting or unrealistic, we measured the common envelope ejection efficiency, this alpha, to be something like 14, which what this means is that the difference in the orbital energy from starting at the common envelope to the ejected common envelope has to be 14 times larger than the binding energy. In general, people who like conservation laws like alpha to be less than 1. So alpha of 14 is problematic, in broadly speaking. That means either we have efficient common envelope ejection, or we have no idea what the binding energy of the donor was. It's possible that that's also on the table. All that said, though, we did measure the kinematics of the kick pretty precisely. So the low natal kick was definitely preferred here. The reason for that is because you can't unbind this wide binary. To keep it bound, you had to have a low natal kick, but you needed some kick to get yourself up to those eccentricity measurements. The fun thing here as well is that you can actually measure that, not unexpectedly, the kick angles and kick strengths were very well correlated, as you would expect. You need to have lower kicks in the direction of the orbital motion. So everything checks out, like, whatever, good. Okay, that's Gaia BH1. We kind of like threw our hands up and said probably it wasn't isolated binaries, because all of these things working together doesn't really bode well for us. Kareem kept doing radial velocity follow-up. This one turned out to be spurious. And so we started working on these, and eventually, my spoiler there, you can see he found Gaia BH2 as well. Gaia BH2 has slightly less well-measured parameters, and that's only because the orbital period is quite a bit longer at 1200 days. Broadly speaking, we didn't go through the whole rigmarole again to make the giant corner plot because it was the same story. Way too big of mass ratios, way too efficient of common envelope ejections. If there was a kick, it had to be very small if it was in the binary. So that's where we stand for isolated binaries and Gaia BH1 and BH2. We did, however, start to hit it with other channels, as we are wont to do in the compact object binary community. We do this with gravitational waves all the time. So in particular, we know that Gaia BH1 is in the galactic disk, so we were pretty sure it wasn't a globular cluster to begin with, but it could have been formed in a young stellar cluster. And so we went to Ugo DiCarlo's work and pulled out everything that kind of is close to it. Problem with young stellar clusters, which you have to run n-body on, is you initialize the population, you simulate it, takes a lot of computation time, it makes a lot of data, and if you rerun the whole thing with a little bit different initial conditions, you get totally different answers, which is like, I hate it so much. It's very frustrating. But we were able to find systems that were pretty close, and in Ugo's group, basically back in Italy with Michele Lupelli, Sarah Rastello did a similar thing, and we basically found if you want weird mass ratio pairings and you want eccentricity in wider binaries, star clusters can give it to you, but only like hand-wavy ways. You're never going to fit things the way that we did with the isolated binaries. Normally that's the end of the story, but this month people went berserk again in the last month. So in the last month, the Gaia team was so excited, they finally realized everyone is excited about black holes. And so they went digging in their data, and they found an even wider, the reason that Kareem didn't find this thing is it wasn't in DR3 to begin with, it's way too wide of an orbit, it's about 11 years. But they found a really weird binary. So if you look over here, Gaia BH3 has 33 solar masses. That's way different than anything that we've seen in the galaxy so far. Kind of. The reason that it's especially way different is because, again, we have this crazy mass ratio offset. The other thing that really sets BH3 apart is that its metallicity is very low by comparison. The wave of excitement continued. A day after the paper came out from the Gaia collaboration, a team in Europe also showed that it actually can be localized to a disrupted globular cluster. So there we go. That's the origin, right? It was in the cluster. That's super easy. That's great. A team in Mark Gielis's group, not Gieser's, actually looked through Kyle Kramer's NGC 3201 model set and showed like, hey guys, look, it totally works. This is great. It all works out. Everything checks out. And then the isolated binary killjoys came in and we were like, you could still make it with isolated binaries. This one you finally can. And so the statement here is you actually can just avoid Roche overflow altogether because it's wide enough. You don't have to do too much torturing of the stellar models. It can just be in its zero H main sequence state, more or less. The black hole is massive enough that we basically don't expect a kick for this thing anyways. We expect a direct collapse. So it's kind of funny that the one that we know is in a cluster, we still tried to come up with an isolated information channel for it. But that said, in a globular cluster, you could just be a binary. It's possible for that to happen. Not very likely, but it's possible. The thing that I want to remind you of is for the isolated binaries, Gaia BH3 hangs out right here. It's right on the edge of this 10-year prediction. I think the thing that is most exciting for me about Gaia BH3 is that there are many black holes with low masses and low metallicity that should be coming out if there's one that's 500 parsecs away from us. And if we start inching this way, we're going to really do a number on our kick models. So I'm really excited to see whether or not we continue to see more of those. I'm really excited for DR4 to come out. It will not be out before the end of 2025, so I think it will be a race for like GWTC4 or DR4. We'll see which one happens. And then the last couple of minutes, I just want to even drop one more set of all of this. I've been talking about neutron stars and black holes, and true to fashion, this paper came out, I think, a week ago. Kareem, in doing his searches for black holes, found everything that there could be in DR4 and started just moving down in the semi-major axis versus orbital period graph. And he's turned out a bunch of neutron star sequence binaries as well. So these are all of the red dots are the Gaia observations. You can see the orbits are just like fantastically well characterized. And again, these are where they stand. So BH2, BH1, and BH3 is like way out off, but of course Kareem didn't find it, so we didn't put that on his plot. These are your neutron star candidates. So you're starting to really get into the weeds. These are definitely harder to characterize. You need a lot more data. Right, and then the statement here, which we haven't dug into in our models yet, but is interesting and probably pretty well expected. The neutron star main sequence candidates stand well above the eccentricities of the white dwarf main sequence candidates. We don't expect white dwarfs to get kicks. We do expect neutron stars to get kicks, so this is nice and expected, but lots of work to be done here, looking at how strong those kicks are. And a final thing that I'll leave from Kareem's paper, which I think is quite interesting, is we're starting to get a lot of detections in the galaxy, and like this mass gap is like really maintaining itself. You can do completeness cuts, like selections in Gaia DR3, and if there was something between here with roughly 1 solar mass companions, Gaia probably would have seen it. So we're starting to probe whether or not there is a gap between the most massive neutron stars and the least massive black holes. Gravitational waves have definitely put some things in here, but maybe those are not first generation mergers, right? so far, we can definitely tell you that these come from first generation stars. So that's an interesting thing. And I'll finish with my takeaways. If you're interested in binary stellar populations in any way, and you would like to simulate them, try to download the code or drop me an email. Dormant black hole and neutron stars, I think, are a really unique way to inform binary evolution, because the bright companions bring so much extra information with them. They tell us the metallicities, they tell us the ages, they tell us the positions, and the extremely well-characterized orbits that we just don't get otherwise. And that's all I have. Thanks.
Our own star, the sun, it doesn't seem to have a binary. Any theories around what could have happened to its partner?
I don't think it's crazy to assume that it didn't have a partner.
That's what I'm saying. So what
Yeah.
happened to it?
So if you look at, people are starting, specific people. Max Mo is looking at this problem in detail, and so he's taking data from like Apogee, Gaia, whatever, and he's basically finding that there's a metallicity dependence in the binary fraction, and for our sun to have had a close binary where like we would have seen it, it's about a 15% binary fraction for close binaries at solar metallicity. So the number of close going to interact style binaries at solar metallicity for solar type stars is just actually low. And that appears to be, people are like putting this together, Max and Katelyn Crater. They think it has to do with like literally the composition sets cooling times for the gas and like literally separates you out. And if you don't make binaries at solar metallicity, you actually are more likely to make planets. And so the fact that we exist in this big, beautiful solar system with all the planets maybe suggests that we definitely didn't have a binary, because they kind of bifurcate.
Oh.
Yeah. But that's largely empirically driven. I don't think that anyone was necessarily going down that route until Max said, hey guys, guess what? Like, we did it all. This is definitely what's happening. We need to explain it.
You mentioned that most companions with black holes are older than metal core, and that's because they're easier to observe. I didn't catch the reason.
Yeah, so the reason is because if we're in the business of finding the black hole binaries, you want every single one that is still existing today. And so these ones, even though they formed a long time ago, if you don't have metal core low mass stars, they will have evolved to not be. They're like, you won't see them in the old populations. Like the massive metal core stars have evolved to be black holes already.
Right, but what about low mass metal rich?
Oh, also, yes, those are also coming, for sure.
Oh, okay.
Yeah, it's not I think it's more that, it's a fair statement. This is the new slide. There will be more metal core ones, is I guess what I'm getting after. Because everyone was like, oh my God, I can't believe that it's this metal core companion to the Gaia BH3. And I think the statement is, there will be more systems like these. Because if you take the entire galactic history, there will be mostly metal core stars that were formed, not necessarily like super solar.
I see, okay.
Yeah. Like you add up all of the stars that ever formed in the galaxy, they're all mostly metal core. It's better, actually, I think the thing that's better shows this is Cherok's figure. So this spike, this is artificial because we can't go above cosmic's metallicity limit, and it would be kind of flat, but there's a lot of metal core stars, just because they're all hanging out. This also is the cosmic lower boundary. That's why we get just like,
These are from suns?
These are from, yeah, this is the latte galaxies.
Right.
And so if we had just plotted the latte metallicities that we attached to, it would just be a nice, like, curve, yeah. And this actually turns over a little bit the higher you go, yeah. Oh, yes.
So, sorry, on that side as well, your simulation work is based on Latin, so it's based on the isolated binary scenario.
Yeah.
How would you think the relationship change if you think the cluster binary?
Yeah, so good question. So Kyle did them in his, let's see, where is this? Is that it? So here, they basically look like the ones that we've observed. These, you get, you don't get the super big, well, and actually that's a lie, you do get them. Holy cow, what am I saying? These black hole main sequence stars are in much lower number compared to the black holes at the center. That's the main statement. But they all more or less kind of do what the clusters do in what I showed you with what Ugo did. They can put high mass ratios together that you can't really make in isolated binaries, and they should give you fairly moderate eccentricities. This one, the other thing that's really weird about this one is it's really short period too. So this like maybe was a primordial binary, who knows? But broadly speaking, this is what the clusters kind of like to give you, is a wacky mass ratio, wide eccentric systems, yeah.
Do you know if there are constraints on the types of these black holes from the fact that they're in the cluster?
It's a cluster escape velocity, which, do you know what the escape velocity is of these? 30? 15?
0.20%.
1, 5?
50.
50, yeah. Yeah, so like 60 kilometers per second is
Not the dispersion.
Yeah, not a dispersion.
So then those black holes would have gotten smaller.
yeah, definitely below 50, I think.
That's kind of weird. Is that weird?
I don't think so.
For a 5 solar mass black hole?
Is there actually a real prediction?
Yeah, I think that everyone, I think that we're all really tied to the idea that the kick mechanism comes from pulsars. And I think that that's a problem because the pulsar measurements were done on fastest moving pulsars in the galaxy and the ones that are all single. So they're like by construction of the data set, the fastest, like the biggest kick ones. That's why this is the first thing that I want to do when I stop traveling is back up all of these, measure these kicks, because I guarantee you they're not 265. Like there's no way. Yeah.
Well, I have another question. So is it like there are these 3 black holes in Gaia, and it seems like none of them maybe come from isolated binary evolution. Is that weird? Like where are all the isolated binary evolution ones, or is that like kind of what you predicted?
Here, wait, where did it go? Here. I don't think it's that weird.
Okay, because
Like we didn't expect to see anything. So for us to be picking up this population, it just means that maybe they aren't isolated. But I don't know, God help us with common envelope is maybe the statement that I actually feel deep inside. but yeah, so I'm not particularly freaked out that BH1 and BH2 don't necessarily work. When like BH 25 through 50 continues to not work, then I think that's really gonna pose some issues for us that probably will just mean more job security, I hope. Maria has a question.
So I guess on this same plot, do you have any insight? Like, I assume they're trying to fix whatever issues was. Is it fixed? Do you have inside info? Do you know if they've already fixed it? And what are the prospects in DR4 that whatever the systematic was that made them do this big cut?
Yeah, they'll fix it's fixed. So it actually ended up being these are like beats in the scanning law.
These are what?
Like the scanning law has a period, and these are like it's the orbital periods interfacing like up against the scanning law.
Right.
And so they like shifted, they didn't quite do that, but I think in their analysis, they basically like flipped it. Because they know exactly what the scanning law is. So I think they literally like turned it upside down in their data so that you just like cut like straight through. And not in the data, in the analysis pipeline. There's a like, I don't know, 60-page paper from Barry Hole about this that I can point you to. They definitely figured it out. And it's this data like is in the guided data. Like none of this got actually thrown out. It just wasn't included in the astrometric binaries.
Yeah, I'm really sorry, I forgot about the people on Zoom. Does anyone on Zoom have a question?
Let's see. I don't see anything in the chat, but raise your hands.
No.
Yeah. Nice.
Is cosmic two triples?
No. It says cosmic two triples. Never. But I can point you to code the two.
Yeah, and there's a CITA fellow coming in the fall with this, triples, common,
Nice. Yeah. Yeah,
so
cosmic
can you
is,
come back
yeah, isolated forever.
How important is it about the triple side of things? High mass stars, even the triple fraction,
Yeah.
it's really high.
For high mass stars, I think it's probably a problem.
It's like,
That's my biggest fear, if we're like talking about a therapy session right now. My biggest fear is that this is everything. It's open clusters, and open clusters are just totally packing up everything. And we're never gonna learn a single thing because all the massive stars are born in open clusters. That's like the devil sitting on the back of my shoulder. I hope that this is not the case, but.
the devil is good.
Yeah, but what I can say is I don't think that triples will save you. The triple fraction is high, but also the quadruple fraction is high, and the cluster fraction is high. So it's, yeah, isolated binaries are bust is still my statement. If it becomes the case that I can't do anything with massive stars, I will just like crab walk back to the wakeboards, because I think we're safe with the wakeboards.
Okay, I think, yeah, there's, upstairs, there's like post-seminar snacks, and discussion, so, yeah, we can continue.
Thanks. One day, I will finally use your chair. What I think we should do is, the way that Tom Wag grabs older data, we should already do that with them.
I can easily give you a full mock note to it. Last time I gave you a mock Apple data set for the analogy, but I wanted to see like the right
Yeah.
Yeah, and just unrelated this question. I think Karim has a paper that says that white dwarf gets tiny kicks based on their exception distribution.
Maybe.
Yeah.
It's, I don't think that that's the only answer for exogenous. I think that's what my